Okay. Okay, so yeah, so now, okay, so poof, I have no idea what went wrong. So, but anyway, well, so let's see. So I have no idea. I didn't change anything on my settings, but I could manage to. And I don't know. So now here we are. So then you all missed the discussion of the questions. But anyway, so the questions were a little bit ill-posed. My original intention was to pose a little bit different questions. I wanted to pose the question the way that C is a subset of R2, so maybe having coordinates x and y, and x is supposed to be positive, so the right half plane of R2. But the question makes sense like this also. Yeah, so then let's go through it pretty quickly. So first is yes, of course you can separate these two sets. In the real line, the separation is just given by one number and the direction, but yeah, probably the direction doesn't make any difference. So you just need to designate the cutting point. So the p is always maybe just the number 1, and the alpha is just the cutting point. And of course, you can separate these two sets by taking the cutting point 0. Then it's still a valid separation. And by the way, I keep making errors here. Separation should be an A here, not an E anyway. So strict separation may not be possible, for example, if C is the full set of non-negative numbers here. Then the only way to separate this set from 0 is at 0, you cut at 0, but this is not a strict separation. So it may be possible, but in general the answer is no. But proper separation is always possible, because the set C has to contain non-negative numbers. So, and then what you just need is that the inner products, and this time just the product with one of the element in this, there's one element here and the one element there, such that the respective inner products really actually differ. And of course they do. The inner product is here is 0, so with 1, so one inner product is 0 and the other is strictly positive. So, and if we assume that 0 may even be contained in the set X, then we still can separate, of course, but proper separation may not be true anymore. So this is actually not true, the last option. This is also not true, because C may then just well be the same set, just containing 0, and then you can properly separate them. Okay, so nice. So now what I also wanted to add is, of course, you can during the lecture, in case anything is unclear, or you can't read anything because my handwriting is there's still room for improvement, I would say. Or you would like to have a question, or just interrupt me in chat. So, okay, topic today is convex functions. And convex functions will always be defined in our case on RD. In general, again, if you want to have it, you could have a real separable Hilbert space here, but anyways, but the image space should always be something like the real line. So we need an ordered image space, because we want to compare values. F of x should be compared to f of y for different points x and y. So we need something which is ordered here. But actually we will not work like this, but we will extend the real line to include the values plus infinity and minus infinity. So this is just R, and we add two elements, infinity and minus infinity. And then we need to discuss what algebraic structure should be put on this set. Of course, this will not be a field anymore, but we will not need any field properties here, but we need a few things. So how should we do arithmetic in the extended real line? So, and there are a few things. So what we need to define is addition and subtraction. So of course, for two real numbers, anything should stay as it is. A plus b is again the same as a plus b for two real numbers. But what we need to define, what is a plus infinity? And of course, this should always be the same as infinity plus a. And we'll define it as infinity if the a is actually not minus infinity, but it may be anything else, even infinity. So infinity plus infinity should stay infinity, and infinity plus a real number should also be infinity. Okay. Similarly, if we want to subtract infinity, this should be the same as having minus infinity plus a. This should always give minus infinity, not always. In the case we do not define as so this is important and this is important. So for this to hold, a shall not be minus infinity, and the similar here, for this to hold, a should not be plus infinity. Okay. And what about a times infinity? This should of course be the same as infinity times a, and should be infinity. And similarly, a times minus infinity should be minus infinity times a, and should be minus infinity. But so multiplying infinity by some number should kind of give you the same type of infinity if a is positive. That's yeah, if a is positive. Oh yeah, yep. If a is positive and may even go up to infinity. If a is negative, down to negative infinity, this should be kind of the same but with a flipped sign. So then a times infinity should still be the same as infinity times a, but then we should get negative infinity if you multiply by a negative number. Here the other way around, this should be then give infinity. These two things hold for negative numbers. And what do we do with 0? This is kind of ambiguous. So this all makes perfect sense, I would say. There's nothing one could sanity one could do anything else yeah, in the same way. But for this thing which is 0 times infinity, and there you can really have a choice. So it would make sense to have a 0 or infinity. Both kind of are sensible. But here in convex analysis we would do it like not times a times 0. We will say this is 0. Actually, I'm not sure how often this really occurs, but let's do it like this. So 0 times minus infinity is the same. So if we take one of the infinities times 0, we should always get 0. Okay, and so the negative of negative infinity should be plus infinity. And another convention is that if you take the infimum of the empty set, this is kind of the smallest number, which is larger than nothing. And this holds for any number, so this is plus infinity, and similarly the supremum is then minus infinity. Okay, and caution is always so what do we not define is something like infinity minus infinity, and minus infinity plus infinity is not defined. So we made a decision here where we said 0 times infinity should be 0 in our case, so but we do not make any decision about this. Infinity minus infinity, this will only lead to problems if we make a decision one way or another. Whatever we do, we're going to get problems at some way. So okay, but we always have these kind of functions now with this extended real line, and you're invited to check everything which I write down, and check if I didn't make any mistake, if there's anything occurring which is not actually defined here. Oh, and I forgot one thing. It's also not in the lecture notes, but probably that's clear. We also say about the ordering that for all a in the extended line, it holds that a is smaller or equal to infinity. So if you put in infinity and order it into the real line, extended real line, infinity is the largest element and minus infinity is the smallest element. And as soon as a is a real number, then we even have strict inequality. So this is how the ordering is going. And because the main thing we want to do is we want to do convex combinations of function values and compare them. So I think with these rules we will be fine. Okay, a special function of this kind is the following. If we have S is a subset of Rd, or more generally the domain of our F, we define the so-called indicator function. Indicator function is, I use I for indicator with the subscript of S for the set. That is then a function of this type to the extended real line, and we're going to have the following. It kind of indicates if we are inside or outside the set, and like characteristic functions doing this by assigning the values 0 and 1. We do it differently. We assign the value 0 if x is an S, and infinity, so plus infinity if x is not an S. So that's the so-called indicator function. It indicates if you're inside the set. Inside the set, the value is 0. Outside the set, it's plus infinity. So if we have, if our set looks like this, for example, then the function is 0 here. There it's not 0, and then it just jumps up to infinity. So, and this is how I picture these functions with values plus infinity, and at the point where it jumps up to plus infinity, I indicate it like this. That is from point here on, the value is plus infinity, so we can't see anything anymore. Okay, so now this has been a bunch of definitions, but this is now the first official definition. And so a function f mapping Rd to the extended real line is called proper. If f is never assumes the value minus infinity for all x, and there exists just one x0 such that the value of x of f at x0 is finite. So proper functions are never minus infinity, and at least at one point they are finite. So the function, any function which assumes minus infinity at some point is not proper, and also the function which is constantly plus infinity is also not proper. Then we have the so-called effective domain, and this effective is usually omitted. Domain of f, it's written by DOM as always. That's defined as all the points x such that f of x is not plus infinity. So, okay. So we have proper, we have effective domain denoted by DOM, and now comes the more, these are kind of very straightforward notions. What is a little bit less straightforward is the notion of lower semi-continuity. So f is lower semi-continuous. So it's semi-continuous from below. And this is always abbreviated by LSC. LSC, just like CVX stands for convex, LSC stands for lower semi-continuous. At some point x0, if, and I just write it down and then we're going to have a look at it. If f of x0, so the value at the point, is smaller or equal to the lim inferior, so the lim inf of f of x, whenever x tends to x0. So this is the notion of lower semi-continuity, and you note probably two differences with respect to standard continuity. Continuity, you would have an equal sign and the limit here. So in this case we have lower gives you the inequality, and semi probably comes from the lim is inferior. Okay. And then of course, not write it down here, if the function is LSC at every point, it's called LSC in general. Okay. So, good. So there's two equivalent descriptions, and there are more equivalent descriptions. One which are pretty obvious is f is LSC at x, 0 if for every lambda such that lambda is smaller than f of x. So probably I should write like this: for every lambda smaller than f of x, there exists a negative epsilon, a positive epsilon, such that whenever such that f of x is larger than lambda for all x in the epsilon neighborhood of x0. Oops. Okay. That's weird. Okay. So that's an equivalent condition. It's not totally straightforward to see, but it's not that difficult actually. So whenever you're below, you can get above. And another condition is f is LSC at x0 if f of x0 is smaller or equal to the limit, not the limit inferior, whenever x tends to x0 of f of x. I think it's written like, so no, not like this, like you take a sequence, xk going to x whenever, so we're taking the sequence xk, let k go to infinity, and this should hold whenever xk tends to x0 and the limit exists. Okay. That's probably more straightforward to see. Yeah, intuitively it looks like the function may jump down in the limit if the limit exists. So here, if the limit exists, so you have a sequence xk converging to something, you look at the function values, and if the function values do converge, they have to jump down in the limit. They can't go up, but they are allowed to jump down. So here's an example of a function which is lower semi-continuous, continuous. So let's say it goes like this here. At this point, it jumps to something else, and then it does something else. Yeah, and then where can I put the function value here at that point such that the function is lower semi-continuous? So it will never be continuous, no matter what I do, because it kind of, if I converge here, the function value is not here, then I have a problem. If I come from here and the function value is not there, I have a problem. It can't be here and there at the same time, so I always have a problem with continuity. But for lower semi-continuity, I only need that I can't get, I'm allowed to jump down. So I can put the value here at the lower end. If I do that, and here this indicates the function value is not here, but it's there. And so if this now is our x0, then we are actually lower semi-continuous at the point. So if x goes to x0 from the right, then the function values are decreasing in what I've painted here, and they are decreasing down to that value. So if x goes to x0 from the right, so or xk goes to x0 from the right, then the function values are actually decreasing. But to this value, and the function value is even smaller. And of course, this limit here need not exist. If the xk's go from the left and from the right or something, then this sequence here will actually never converge. But the limit inferior will still exist, and it will be probably this. If you have infinitely many from the left, it will still be this value here down here. Okay, this is an example as a graph, and an example by formulas. For example, let's say if we have functions from the real line to the extended real line, then let's say if we take the indicator function of something like a half open interval, this is not LSC because we can converge from the left to -1. F of xk will always be plus infinity, but the limit but the function value at the limit point, the function that was from the right, from the wrong direction. The function value at the limit point is also infinity. That's fine. But if we go to -1 from the right, this f of xk will always be 0, but the function value at the limit point will be plus infinity. So we have jumped up in the limit, and this is not allowed. However, if we take a closed interval here, this is LSC, so even if it's not continuous, it jumps up to plus infinity at the boundary, but the values are down. Another example would be f of x is equal to 0 if x is 0 and 1 else. So this here I would this would look like this, and how I would draw the graph. Here it would look like this. Here it's -1, and 1, and it's always down there. And here the function would probably just look like this. This is also a lower semi-continuous function, so the only point of discontinuity is here, and there we just jump down. Another thing what we could do is take the function 1 over x for positive x, and then say we stay at plus infinity over here. So and the graph would be just like, so here we go like this, and here on the left hand side is always the value plus infinity. But it's still okay if you the point, so in here we don't have any problems because we are always at infinity. This inequality is just always infinity less than infinity. And here in the only point of this, so this continuity, it's still fine, because if you want to converge to here, if you come from the left, it's clear that we're at plus infinity. If you come from the right, we always diverge to plus infinity, which is still fine. So this is LSC. And this is also LSC. Okay, that was one notion. Still not talking about convex functions, and the next definition is also not about convex functions. So the next definition is the epigraph. The epigraph of some f from Rd to the extended real line. This is denoted by epi of f, and I haven't made up my mind if I should use parentheses here or not. Probably I will do both. So the epigraph is a set of tuples x and alpha, which are x is an Rd, something which you can plug in here, and alpha is a real number, something which may come out here. And the condition for the tuple x alpha to be in the epigraph is that the function value is at x is smaller or equal to alpha. So what is this? That's actually, or maybe I'll just paint it here. So what is this in this big example here? It's actually, the epigraph is a subset of the product. So domain of definition times range. So it's a subset of this plane here. And it consists of all the points such that the alpha is above, it's above the graph. So actually everything which is here, that is the epigraph. And maybe it's still interesting what happens here at this point. What about this line of connection here? Does it belong to the epigraph or not? And this now depends on where the function value is. Is it down here or is it up there? In my example, the function value is down here, so this line actually belongs to the epigraph. And also this line here belongs to the epigraph. We have only smaller or equal to, so this line is also part of the epigraph. And even this jump line here is part of the epigraph. That's actually pretty important, and you may even see now that the kind of the properties of the epigraph may encode the lower semi-continuity of the function, and it does. So the level sets is another thing. Level sets of f for some alpha in R. This is denoted by lef for level, the lower alpha for the level, f for the function, and this is just also, this is just a subset of Rd, it's not tuples. This is just x and Rd such that f of x is smaller or equal to alpha. So in is okay. So if we put here some alpha, this is our level, then we should collect all the x's which map to something which is smaller than alpha. So we consider a line like this, and then we look down here, and so in this case this interval here is the level set. This here is left alpha of f if this is alpha. Okay, and then it's now again interesting to have a look at what happens if the level is something which is crossed by a jump. If you now draw the alpha line over here, and you see this point here may or may not be in the level set depending on where the function value at this jump point is. If the function value is up here, the x0 does not belong to the level set. If it's down here, it does belong to the level set. So this, if it's open or closed here, the level set depends on where the jumping point is. So also it seems like the level sets do encode information about the lower semi-continuity, and actually they do. Yeah, and that's even the content of the next theorem. It says that, come on, what's wrong here? It says that the lower semi-continuity can be expressed by properties of the epigraph of the level set. So if you have f from Rd to R, then the following are equivalent. The first condition is f is LSC. The second is the epigraph of f is closed. And the third is for all alpha and R, it holds that the level set with respect to level alpha is also closed. So lower semi-continuity is equivalent to closeness of the epigraph and also to closeness of all level sets. Okay, that's nice because it really nicely links this continuity property here with the topological property of the set epigraph. And actually what is also clear is that the epigraph kind of encodes the function f totally. So if we know if we see a set and know it's an epigraph, there's just one function from which that can come. And for a set to be an epigraph, if it's just the condition that if some point is in there, everything which is above it is also in the set. So the subsets of Rd times R, which are epigraphs, are also very simple to spot. It's not hard to see which is an epigraph and which is not. Okay. So what's the proof? How does it go? Okay, so here's the theorem still, and so what is the proof? Okay. Of course, we make a circle of implications. One implies two. So f is now lower semi-continuous, and we need to show that the epigraph is closed. And in our case, we always work with ordinary, so with sequential closeness. And if you would now work here in a Hilbert space, things would be different. So because in a Hilbert space, you would have two different notions of closeness and even different notions of convergence. There's strong and weak convergence, and there's also strong closeness, weak sequential closeness, and even weak closeness, and they are all not always the same. So, but here, closeness is the same as sequential closeness, so it can be checked by sequences. So what we do is we take a sequence alpha x and alpha n converging to x alpha. That's a subset. It's a sequence in R to the d plus 1, and we assume that xn alpha n is always element of the epigraph. And actually there was a typo in the lecture notes. I forgot this n here. So what you need to show is that the limit point also belongs to the epigraph. That's what we need to show. So first recall, what does it mean? xn alpha n in the epigraph, it means just this: f of xn smaller equal alpha n. Yeah, but now actually it's okay. Now we have LSC. So f LSC gives us that f of x. Now, of course, so if this holds, then xn converges to x and alpha n converges to alpha. That's how it works in d plus 1 dimensions. So, and then by LSC, the function value at the limit point is smaller or equal than the limit inferior of f of xn, which is, in this case, we can just drop the inferior here because the sequence sorry, that was wrong. We can't drop it. But what we know is this guy here is always smaller or equal to alpha n. So we can upper bound it by replacing this with alpha n, but the alpha n actually converge. So now we have here limit of alpha n, because that was our assumption that they converge. And this is actually equal to alpha. This is also what is up here. So we have the function value at the limit point is smaller or equal to the alpha, and this exactly means that this tuple x alpha is also in the epigraph. So that was simple. And it nicely illustrates so that our geometric intuition here above is totally accurate. If it's lower semi-continuous, then the epigraph is closed. Okay. 2 implies 3. Two implies 3. So epigraph is assumed to be closed, and we want to show that the level sets are also closed. So what we do is we take xn converging to xn in the level set of some alpha, which means that xn alpha also converges to x alpha, and and that's it already. So the xn is it yeah, actually already, yes. So and so if this is in the level set, it's also in the epigraph. And by the closing of the epigraph, we see that x alpha is also in the epigraph of f, and this actually means that x is in the level set of level alpha of f. So that's totally straightforward. I think we could also just say that this level set is the intersection of two closed sets. So it's the epigraph and this cutting line. So now to close the circle, we also show that 3 implies 1. So we assume that the level set of f is always closed for all alpha, and we take an x0 in Rd, and then we have first one special case, which is if the function value is equal to -infinity, then f is always lower semi-continuous at x0. That is just nothing to prove, because for lower semi-continuity, maybe I can put it up again, if this is -infinity, this inequality is always fulfilled. There's no way it cannot be fulfilled. So if we it's just like that. So let f of x0 be larger or equal -infinity. So not -infinity. Okay, so then what we do is we assume we take an alpha which is now smaller than f of x0, and this says that x0 is actually not in the lower level set of f for the level alpha. So now this level set alpha f is closed, so its complement is open, and hence we can see that there exists an epsilon non-positive such that the level set of alpha does not intersect the epsilon ball around x0, and this means that f of x is larger than alpha for all x in this ball around x0, and this says f is LSC at x0. Okay, so that's lower semi-continuity. It's nicely characterized by closeness of the epigraph or closeness of all level sets. Okay, so that's one thing. It's a good characterization. And the next thing we want to know about lower semi-continuity is how does it behave with operations on the functions. So next proposition, what can we do with functions without destroying lower semi-continuity? So we take a bunch of functions, f, g, and also a family of LSC functions, fi, all from Rd to the extended real line. All of them are LSC, and A is a D times M matrix. Alpha is positive. Then the following are also lower semi-continuous, and this is okay, so there's all another typo. So the first condition is that f plus g and alpha f. Okay, no, f plus g, there's one problem. f plus g may not be defined. And there's one problem which may occur. If f assumes the value plus infinity at some point and g assumes minus infinity at the same point. If this is true, then f plus g cannot be defined because we did not define what plus infinity minus infinity is. So this is only if defined. And of course alpha times f is also lower semi-continuous for non-negative, for positive alpha. The second is that even if we precompose a linear map, that doesn't do anything. The third point is if we take the infimum of two functions, the point was infimum, it still stays lower semi-continuous. And the fourth one is if we take the supremum of arbitrarily many functions, it's still lower semi-continuous. Okay, so and yeah, this is clear by assumption because the limit inferior is subadditive, or by just saying, yeah, that's just is. So this is clear by definition. It's also clear by definition, and it's also clear with this alpha negative. If it does not hold, because the minus sign goes out of the limit inferior, it turns into a limit superior. And so this is also clear if we precompose a linear map, nothing going to change. So it just computes with the limit. So for the infimum, we just draw a picture. If this is f and this is g, then what is now what we can show is one way to show that this function is LSC is seeing that the epigraph of this function is closed. So the epigraph of f is all which is here, and the epigraph of g is all which is here. The infimum function is actually this one here. So it's the union of the epigraphs. So writing it down here, this follows from the epigraph of the infimum of f and g is equal to the union of the epigraphs. So the union of closed sets is closed. And this also says what's happening here. The epigraph of the supremum of something. So in this case, it's only what's here. So the supremum is in this case that function here, and this is then the intersection of all the epigraphs. So an intersection of closed sets is closed. And that's it. So that's quick as that. Okay. So let me check. So I'll probably do this and that, and then we make our short break. Okay, so lower semi-continuity is preserved under a few conditions. And that's probably interesting here, because this says somehow that as long as it's always defined, the lower semi-continuous functions seem to form something like a cone. We can multiply by non-negative numbers, and then we can add. So if we say from the beginning that the function value should always be larger than minus infinity, so minus infinity is never allowed, so for proper functions. So the set of proper lower semi-continuous functions, they actually form a cone. Okay, that's nice. Okay, and this is also, we're also going to use that. So, so if you have a non-continuous function, there's not really much you can do to the function to make it continuous. So if you have a function which is with a jump, there's no way you can just force the function to be continuous at a point by a minor change of the function. You have to do a major change. That's not true for lower semi-continuity. For lower semi-continuity, there's always a way to do very little to the function and make it lower semi-continuous. So for what we can do is, so we can do the lower semi-continuous hull, the lower semi-continuous hull of f is defined via its epigraph. as and it's the epigraph of the hull, which is noted by F overline, is just the closure of the epigraph. So short illustration, if our function is like this, that it jumps somewhere, and it's actually not at the lower end, the function value at the jump, then in this case the epigraph is just everything up here, that point, that line, and that line, but this point not, and also not this line. So in this case the function jumps up here, the epigraph is not closed, and the problems occur at the jump. But if we now take the closure of this red set, what do we add? Yeah, we just add everything which we can reach with convergent sequences, so we can converge to everything which is here. So closure actually adds these things here. This is what we're going to add, this line and this point here. And it stays an epigraph. That's important. It stays an epigraph as a function, and if we have such a set, we can define the corresponding function. If you want to know the function value here, we just take the infimum over all the alphas and such that x0 alpha is in the epigraph. So that is the lower semi-continuous hull. And I think there's a little problems here with functions which do assume the value negative infinity. And because of this, there's a little bit, there's one special case, so that we don't use this lower semi-continuous hull, but something which is a little bit more general, because it also deals with the value negative infinity. So we define the closure of a function. It's slightly different. So closure of f is defined as either the lower semi-continuous hull if f of x is larger than minus infinity for all x, or as minus infinity if the value is actually minus infinity for some x. So as, if we have the value minus infinity at some point, the closure shall always be the negative infinity constant function, and in case minus infinity is never assumed, we just take the lower semi-continuous hull. Okay. Okay. And of course the function is closed if the closure doesn't change the function. Okay. Okay. Yeah. Short example. 4.6. If we take f as some indicator function, let's say from the open interval a b, then the closure of f is of course also the lower convex, the lower semi-continuous hull, and this is the indicator function of the closed interval. It's just simple as that. You just move everything as low as possible. Okay, yeah, so intuitively, what does the lower semi-continuous hull? At all of the jump points, it puts the function value as small as possible without destroying the lower semi-continuity. Okay. Good. So, time for a short break, and after the short break, we're going to continue with the notion of convexity, finally. Okay. So, there's a small break here. See you in 2 minutes. Okay, so I'm back and here we go. So, okay, so and I think we don't have to hurry that much anymore because I think we can cover the rest in the last half hour. So, finally the definition of convex function. So this definition for 7. So, and now if we have a function from Rd to R bar, then we say what this function is, and first point is it's convex, and we basically do it like convex sets. We could define it like saying that the epigraph is convex. The epigraph is a convex set, which is would be a valid definition, but I guess it's sensible to write down the usual definition, and this says a convex if you have x and y in the domain. Yeah, I think it's better to have them in the domain, in the effective domain, and we have some lambda in the interval -1 to 1. Then it should always hold that f at the point lambda x plus lambda x plus 1 minus lambda y smaller equal lambda f of x plus 1 minus lambda f of y. That is the usual definition of convexity. And of course, you should draw the picture here. Convex functions look like smiles somehow, and if you have an x here and a y there, you have the function value f of x here, function value f of y there, and this is always a point in between. So somewhere here, let's say there, this is the function value there, and it says the function value here should be smaller or equal than the corresponding convex combination of the function values. And if you think of lambda varying from 0 to 1, you go from here to there in the kind of linear fashion, and you also go from there to there, from there down to there, and actually move along that line here. So, so this number here is actually the number up here. So this here is the right-hand side, and this here is the left-hand side. So this is that impression here. So this is always should always be larger than this. So meaning that this the so-called secant is always above the graph. Okay, that is the standard notion of convexity, and probably you already know that. A few strengthenings. There's something, say, a notion called strictly convex. First comes strictly convex. Strictly convex. If you always have strict inequality whenever x is not y and lambda is not at the boundaries, and lambda is in the open interval. So we always have this inequality here strict as soon as the points are not the same and the lambda is not at the boundaries. Because for lambda at the boundaries, one of these things vanish, and there's always equality, and the same if x is equal y, you also have always equality. You can't do anything about it. But as soon as you exclude these few cases here, you want to have strict inequality. Then there's a little bit more. There's called uniform convexity, uniformly convex. If there exists a phi strictly increasing with function value 0 at 0, so it's enough to have it from the non-negative numbers to the real numbers, strictly increasing with phi of 0 equal to 0, such that you always have f of lambda x plus 1 minus lambda y smaller equal lambda f of x plus 1 minus lambda f of y, and then here comes minus, so we can even subtract a little bit. The little bit depends on a few things, and what we need here is this lambda times 1 minus lambda times phi of the norm difference. So it's even more than strict convexity, because we so if this is true, we see that we always have strict inequality as soon as x is not equals y, because then this is non-zero in here, so the phi is actually positive, and we really subtract something as long as lambda is not at the boundaries, and we kind of uniformly do so. No matter where x and y are, there's something which we always subtract, which depends only on the distance between x and y. Okay. And there's the notion of strongly convex, which is it's not really more, but it's more concrete. Strongly convex, with constant sigma non-negative. This is strongly convex. If it's uniformly convex for the function sigma squared over 2. So, but I write it down here. And the same assumptions if f of lambda x plus 1 minus lambda y smaller equals lambda f of x plus 1 minus lambda f of y minus lambda times 1 minus lambda times sigma over 2 square norm of x minus y squared. It's important. Okay, so you see strongly convex basically means uniformly convex with respect to the function sigma over 2 times argument squared. Okay, these are the different notions of convexity which we're going to use. One remark is, so f is strongly convex with constant sigma if the function f of x minus norm x squared over sigma norm x squared over 2 is convex. So if you can even subtract from f a square, the scaled norm square, then it's strongly convex with the constant which is in front of sigma squared over 2. Okay, so that is one point. Could be a remark. And another remark is, of course, strongly convex implies strictly convex implies convex. The reverse implications do not hold. For this you can consider, for example, an indicator function of a non-empty interval, but also linear functions would work, affine functions would work, and this is also not true. A function may be strictly convex, but then it's still not necessarily strongly convex, and there you can consider the function f of x is x to the 4. Okay. Maybe okay. Yeah, this is not strictly convex. It's not so straightforward to see. Okay, that's another remark. We have these implications, and we have this characterization of strong convexity. And there's one more. If f is convex, then the domain of f is also convex. So the set of values where the function is not plus infinity is also a convex set. And for some reason I miss the result. I don't know where it comes. It should come somewhere. Namely that a function is convex. A function is convex if and only if its epigraph is convex. And with this, we can nicely talk about proper lower semi-continuous convex functions, because the function is proper, convex, and lower semi-continuous if the epigraph is non-empty, convex, and closed. And so properness of the function corresponds to non-empty epigraphs, excluding the value minus infinity. Lower semi-continuity of f corresponds to a closed epigraph, and convexity of f corresponds to a convex epigraph. Okay, and by definition we call f concave if minus f is convex. But concavity will not play a role here in this in the full lecture as far as I see. No, I don't think so. Okay, And then there's still there's two results to go, so two lemmas, which we're going to need. The first lemma is straightforward to prove by a simple induction, but it's pretty important. It's called Jensen's inequality. You probably also know that, I don't know, from stochastics or wherever. And it goes like this: a function f from Rd to the extended real line, and this is convex if and only if for all xi in the domain of f and lambda I in the interval from 0 to 1, such that they sum up to 1. It holds that the function value at the convex combination is smaller or equal to the corresponding convex combination of the function values. So for this is here in n. So for n equals 2, this is just the definition of convexity. And now you can prove it by simple induction. If you consider the case n equals 1 is clear, because then lambda is 1, that's done. N equals 2, it's the definition of convexity. And if you have n larger than 2, you can just separate one of the lambdas out and call it lambda 1, and the others are then n different lambdas. You need to normalize them by 1 minus lambda 1 and then apply the induction hypothesis, and then you're done. And maybe I just write it down. So the proof is totally straightforward. So n equals 1 and 2, that's done. And now the induction step, it goes like this. You write something like this down. You take lambda 1, x1 plus I goes from 2 to n plus 1 lambda I xi. And here you rewrite it as plus, and then you here put 1 minus lambda 1, so you get a convex combination, and you of course have to remedy this here by dividing by 1 minus lambda 1. So this is lambda 1, that's lambda 1 too. Xi, and then you apply the case for n equals 2, lambda 1 f of x1 plus 1 minus lambda 1 f of that guy here. Because why does no this okay, that's done already. So this n equals 2, and now here by induction hypothesis, these guys here sum up to 1, right? This is actually constant. You can put it out of the sum. The others sum up to 1 minus lambda 1, because all of them sum up to 1. So here you small a equal to that. And now it's done. And now this cancels again, and you're done. So that's the proof of Jensen's inequality. Okay, so probably we're going to need it, but actually it's also true for integrals over domains with kind of measure 1. Okay. So if we replace this sum here by an integral over domain with measure 1, okay, but anyway, then it works. Okay. So then there's the last lemma. Actually this was lemma 4.8, right? This was lemma 4.8. And the last lemma is lemma 4.9. Yeah, we have quite just enough time to do that. Lemma 4.9, it's a little bit strange, but it's also helpful for us, because we had these two function values, plus infinity, minus infinity, which behaves a little strange, and you already seen that in the notion of closed and lower semi-continuous hull of functions, we had to deal with the minus infinity in a special way. We also have to deal with plus infinity in a special way, for convex functions it's a little bit simpler. Many books on convex analysis do not even treat the case that functions may assume the value minus infinity, and the reason is the following lemma. So if f is convex such that f of x0 is finite at some x0 which is in the relative interior of the domain of f. So it's not only that f is finite at some point, but the relative interior contains a point where it's finite. Yeah. Then f is proper. And the only thing which we only need to show, so properness means it has a finite value, but it never assumes the value minus infinity. So of course we have a finite value, it's already there. So this conclusion here only means, i.e. it does not assume minus infinity anywhere. So this is nice. So if we take talk about convex functions, they may be always minus infinity, but as soon as they are finite at some point in the relative interior of the domain, they may not be minus infinity anywhere. So if you have a finite number, okay. Okay, so let's prove it. So okay, for contradiction, so you argue by contradiction. So by contradiction, assume there is an x1 in the domain of f, such that f of x1 is minus infinity. So, but we have this point x0 in the relative interior. So since x0 is in the relative interior of the domain of f, we can use what's called proposition 1.8 and the point 3. This implies that for all x2 in the affine hull of the domain of f, there exists an epsilon such that x0, and I take plus epsilon, x2 minus x0 is in the domain of f. So finite, and we just, so this was proposition 1.8, third point. It actually was an if and only if, and it's also with a minus, but we only need this implication with a plus. So what we can do is we can call this guy here x1. Wait. Sorry. This was x1, and we call this guy x2. Yeah, I messed up a few indices here. I guess it's still true what I've written here. Let me see. So we call this guy x2, and this is then... Oh no, sorry. For all x2, this is 2. For all x2, this is 2. Okay. Okay, so what we don't, okay, we choose this point such that this is actually x1, and if we do this, we can rearrange to the fact that the equation x0 is equal to 1 over 1 plus epsilon times s1 plus epsilon over 1 plus epsilon x2. So this is just then a convex combination. So we just take this as lambda, then this is lambda x1 plus 1 minus lambda x2. So we can then write this x0, which is in the relative interior, as the convex combination of one thing where the point was minus infinity, and the other point x2 is still in the domain of f. In the We can do it for all points x2, and so we can do it especially for the points in the domain. Okay. Okay, so when we take x2 actually in the domain of f. So and then by convexity we get that f of x0 is smaller or equal to lambda times f of x1 plus 1 minus lambda f of x2. However, x1 we have minus infinity, and here we have a real number because it's in the domain. And one more thing is, I forgot to say epsilon is larger than 0, so this here the lambda is actually strictly between 0 and 1. So this thing here is especially larger than 0. This is larger than 0, and so we have by our calculus rules that this is minus infinity. Okay, so this is a contradiction to f of x finite. So yeah, maybe that's enough. Maybe that's that one. I think one can draw a nice picture, but I don't try. Okay. Okay. So and then, yeah. Okay. Few examples for convex functions, and there are more examples to come in the next lecture at some point. So first example is affine functions are convex and concave at the same time. So minus an affine function is still an affine function, so it's still convex. And moreover, the affine functions are the only functions which are convex and concave at the same time. So if a function is convex and concave, it has to be affine. Okay, second point is f of x equals norm of x, convex for all norms. Okay, that is also simple to see because yeah, it's you just plug in a convex combination and then apply the calculus rules for norms, and you'll see it will be they will be fulfilled. But however, none of these norms is ever strictly convex. No norm is strictly convex. Strictly convex function, I say it like this. And this is easily seen if you take y equals 0 and x non-zero. Then you have that lambda times x plus 1 minus lambda times y is actually, so this is 0, this is only lambda x, this is actually lambda times x, so of course lambda need to be in the interval from minus 1 to 1. So if this is 0, this is just this, so lambda goes out, it's positive and non-negative, so it goes out like this, and you can just add 0 once again, and it's still true, but you get an equality. Okay, so no norm is strictly convex as a function. There is the notion of strictly convex norm, which says something different, which says that the balls with respect to this norm are strictly convex sets. So the 2 norm, for example, has a nice round balls as balls, and they are strictly convex sets somehow, but I haven't defined what a strictly convex set is, so okay. But there is this notion of strictly convex norm, but it does not mean that the norm function is a strictly convex function. Okay. Last thing is indicator function IC. They are convex if and only if C is a convex set. That's also straightforward to see that indicator functions are convex if and only if the base set which defines the indicator function is a convex function. And probably I should add this point, I'm not sure if it's, the proof pops up probably in the next lecture, but anyway, as a remark, a function f is convex if and only if the corresponding epigraph f is convex. Okay, so in this sense, somehow it seems like convex functions are kind of special cases of convex sets, because epigraph are special cases of convex subsets of our d plus 1. But anyway, the study of convex functions is so interesting in itself, and there's kind of, because of the additional structure in the epigraphs have, and there's also additional structure for convex functions which kind of do not really relate to their set nature as epigraphs. So I think that's it. And as expected, no, that's not expected. So I still well before 1. Nice, even though we had these technical quirks in the beginning and the stream kind of did not show up, still managed to stay in time. Okay, that's it for today. And next lecture will be next Tuesday. Okay, in case you have any questions in between, just post your questions in chat, and you'll get an answer as soon as somebody is on duty. Okay. So I see you next Tuesday.